Good afternoon, everyone. Today we'll be talking about vertical transportation system design parameters. I'll quickly run through the short agenda that we will cover. We've had our welcome from Paul. I will discuss the design parameters and we'll have a Q&A session at the end. The vertical transportation design parameters I will be discussing are the basic parameters we use to determine how many, how big, and how fast to be in any specific building. Which are used within the systems and what they actually mean in any system. The main ones for determining elevator performance are handling capacity, which is the maximum percentage of the population that can be transported in a 5-minute period, sometimes referred to as the 5-minute handling capacity. We also refer to passenger demand. This is the arrival rate of passengers arriving, looking for lift service, expressed as a percentage of the building population. Sometimes the passenger demand is equal to the handling capacity, and at that moment in time, the system can cope. However, should the passenger demand exceed handling capacity, the system will become saturated, resulting in excessive waiting time. The average wait is the average time a passenger will wait for lift service, from either joining the queue or pushing a button until the passenger gets onto the lift. And then we have their time to destination, which is the whole time from pushing the button to getting to their destination floor. To show how these times are linked, this graphic from the CPSI Guide D shows the relationship between waiting time, transit time, and how they add together to determine time to destination. But waiting time can also be taken up of walking time and standing time between call registration and the lift doors actually opening and a passenger boarding the lift. In office buildings, we typically work with a passenger demand similar to this graph, and this graph has been around since the late 1960s, and it models the typical passenger demand of a lift system within an office building, consisting of the morning up peak as people arrive for work, some two-way traffic in mid-morning, slightly increased demand at lunchtime, both up and down, and then a heavy down peak in the evening as people leave work and go home. Lift systems have traditionally been designed around a morning up peak period, which is the worst 5 minutes during this morning peak. And it's been found that if a lift system can manage this peak demand of passengers satisfactorily, the system works perfectly well for the rest of the day. However, in other types of buildings, residential, the peaks are very different. At hotels, the peak typically occurs at check-in time in the afternoon and check-out in the mornings. Apartments, the peaks typically, again, afternoon and evening as people are arriving home from work and then going out for the evening. Residential peak traffic, unlike office traffic, is two-way. Office traffic peaks are typically one-directional. We need to start somewhere, and typically we start with how many passengers. How many people will be looking for lift service? And this is used as the quantity of service determination when we're designing a lift system. So it's important to determine how many people are likely to be in the building, as this will determine our lift system. In estimating office populations, there are a number of formula that can be used. Typically within the UK, we use formulas of 1 person per 12.5 meters net internal area for a typical standard office, or 1 person per 10 meters for a high density workplace. These formulas are typically used by the Building Council Guide to Specification. For residential populations, obviously there are different formulas in determining populations. For hotels, We use this table from CIBSE Guide D, or alternatively, most major hotel chains do have their own brand standards which specifies how many people they want to determine as being in each room and how many rooms will be occupied at any given time. For residential buildings, we use formulas that allow for some factor of diversity between apartments, allowing for the fact that not every apartment is fully occupied all of the time. Our traditional calculations on lifts are based on a model of lifts cycling through a building. At its simplest, this calculation is a sum. It is a simple sum based on passengers entering at the lobby, the lift making a few short journeys up the building as they discharge, and then one long run back to the ground floor. This sum, or calculation, allows us to determine what is called the round trip time. Based on the round trip time, we can determine our handling capacity. And this is because with our round trip time and the number of cars we will assume to be within a group, we can work out how many loaded lift cars can leave the lobby within the 5-minute period, and therefore the handling capacity, i.e. the maximum number of passengers that can be transported up the building within 5 minutes. We can also determine how often a car will leave the lobby, the interval of car departure. And from this, we can make an assumption regarding waiting times for the average passenger. However, traditional calculation is just that. It is a round-trip mathematical calculation, and it's based on probability and some basic assumptions. The results are really only if Franklin's model conform to the assumptions are made. And this is where some of the parameters of system design are critical and how they can affect the results. If we look at simple thing like lift doors, the image on the left shows center opening door panels, whereas the one on the right shows what are called two-speed or side opening doors. Because of the mechanical arrangement in the doors, there is a difference in the amount of time it takes for the doors to open and close. With center opening doors of this arrangement, typically we'd expect 1.7 seconds less for every stop. Now, if in our round trip, this elevator makes 5 stops, that 1.7 seconds adds up to approximately 8.5 seconds. It may not seem much, but 8.5 seconds is the time it takes to travel from one floor to the next in a typical office building. So saving on door time can have a significant cumulative effect. So it's important when you're making your assumptions to make sure they are correct. Another assumption is on car shape. These two lift cars notionally have the same capacity and can carry the same number of people. However, the short wide car arrangement allows for shorter transfer time for passengers. The reason for this is, if we consider a passenger at the very back of a fully loaded car, you can see that they have a shorter journey to the front of the car to exit. They also have to get past fewer passengers standing in front of them. Whereas the deeper car, which is more favored in residential applications, the passenger at the back has to get past more people and has further to walk. Thereby, their transfer time will be slightly increased. Moving on from our traditional round-trip calculation, more and more now we use simulation methods. And simulation allows us to actually model the whole process of passengers arriving, pressing call buttons, entering the car, and getting out. These results provide more than just waiting times and handling capacities, and can also provide greater arrangements and methods to look at what else the lift system does. For example, from simulation results, we can determine queue length. From this example, we can see that after a number of simulations, the maximum queue length is typically around 30 people. Therefore, we would need to check that waiting for a lift. We can also simulate energy use. Energy use in lift systems is directly proportional to the traffic. Because we are simulating the traffic and the number of people moving and their direction of travel, we can determine the actual energy used for a lift system. And from this, we can also use this information to determine our BREEAM credits. Once we have applied all of our analysis, we need to make sure that we are hitting our performance targets. Here, we have the performance target for hotels, which is typically a two-way handling capacity of 12% with an average wait of 40 seconds. In apartments, the target performance is slightly different, and it depends on the level of quality of the apartment building. So, for luxury apartments, we would look to be able to transport a much greater number of people, but they are also expecting a much shorter average waiting time compared with social housing. Overall, the key issue is to try and optimize our design and make sure that the assumptions and the parameters that we have applied do not cause under-design. For example, if we underestimate the number of people in the building, it is very simple to end up with an under-designed system without sufficient elevators. And when the population actually arrives, we will have excessive waiting times, long lobby queues, and effectively the building just does not work. However, if we overestimate populations, it is very easy to end up with an over-designed system, which results in increased core area of the building being taken up for lifts, increased capital cost because we have a greater number of lifts, more lifts will require greater maintenance, and of course, although they're moving less people, because they are moving and many times they are moving empty, there will be increased energy use. So we can see that from this, it's important that our parameters that we use in our calculations are reflective of the building that we are trying to determine the lift system for. Thank you.
Thank you, Hamish. Let's run through some of the questions we've received. Do you think office occupancy will return to pre-COVID-19 levels, i.e. 1 per 10?
Thank you, Paul. It's an interesting question. At the start of COVID, we ran many analysis on how the lift systems would manage with much lower populations and with much lower car occupancies. However, when designing new buildings, we always need to consider that building lifespan. If we think the average lift system for a new office building is expected to last 25 years, we need to design for the traditional 1 per 10 and 1 per 12 populations, because there's no guarantee that we won't go back to that sort of occupancy, or possibly even higher. In fact, just before COVID struck, we were starting to see much higher densities being applied in refurbished office buildings.
Thank you, Hamish. Another question come through here. Surely the design of a building's vertical transportation system should consider the use of stairs?
The simple answer is yes and no. Yes, you need to consider stairs. However, both the Chartered Institute of Building Service Engineers and the BCO Guide to Specification indicate that stair factors and people using stairs should only be considered when the staircase is as attractive to use as the lift system. And by that they mean, is it clear? Can you see it? Is it well signed? Is it open? Is it the sort of thing people are likely to use? In many office buildings, the staircases are typically designed as escape stairs, and you can't actually exit on most floors. So that needs to be considered if you're going to use any sort of stair factor.
Thank you, Hamish. What about the safety of operating program validation?
I'm sorry, I don't quite understand that question, Paul. Could you say it again, please?
What about the safety of operating program validation?
No, I am sorry, Paul. Your sound broke up as you were repeating that.
Okay, I've got another one here. What is our preferred method of looking at off-peak, where the lifts will serve additional floors in the peak express zones? 2, for service elevators, is our preference for RTT assessment.
Right. Again, your sound is breaking up, Paul, but I assume the question was relating to how many lifts serve specific floors during peaks. In general, my personal preference is to have all lifts serving all floors where possible.
Thank you, Hamish. What about absenteeism
Right.
in office buildings?
Absenteeism is accounted for in the formulas that we use from both CIBSE and the BCO. 1 person per 12 accounts for a certain level of absenteeism in that it is an effective density of 1 person per 10. So there is a 20% absenteeism applied, and this is fairly similar across most lift traffic analysis methodologies. You need to be very careful in using absenteeism that you're not just using it to reduce the population being applied to nations.
Thank you, Hamish. I've got another question here. What is our preferred method for looking at off-peak, where the lifts will serve additional floors in the peak express zones? 2, for service elevators is our... actually, I think I've already read that one out, haven't I? Here's another one. How to design for 10% HC with user template and setting of dual time in home floor and other floor in DCS system.
You can use alternative handling capacities by having a custom passenger demand template within your simulation program. Again, though, if you are aiming for performance that is commensurate with BCO or CIBSE, you need to be able to justify your method of analysis and show direct correlation with the requirements of whichever standard you are aiming for performance.
Thank you, Hamish. Another one we've got here. Which kind of risk can take place by operating software?
There are many risks associated with software, and to be honest, Paul, I don't think I have enough time or would be able to provide enough detail on a response to that. So if we can take the questioner's contact details, I would be happy to answer in detail later.
No problem. I've got another question here. What is our preferred method of assessing off-peak, where up-peak lifts are then asked to call at express floors?
Right. There are many methods of looking at how systems work. Trying to second guess the dispatching algorithm can be a difficult and is sometimes fraught with danger. I would tend to allow the dispatching algorithm to determine the best method of serving specific floors, rather than dictating anything like that in a specification. We can simulate it, and again, it would depend very much on the building. It's a building specific issue. So if the questioner has a specific building in mind, please get in touch with us and we can look at it in detail.
No problem. For service lifts, do we assess number of lifts with RTT and distribution of service personnel through the building?
Again, it's a building dependent issue on service lifts. There are guidelines in both CIBSE and BCO regarding the number of service lifts, and from that we can determine typical round trip times, but actual service lift use is very different, and there are no specific guidelines on what waiting time should be expected for a service lift. Typically, service lifts are more about moving goods and are they big enough, rather than can they make enough trips throughout the day.
No problem. I think there's one more coming in here. Let's just see. All right, I think that's. I think we'll take these offline. The rest of these that have come through, Hamish. So thanks again for joining us. I'm sure you agree, it's very informative and interesting webinar. As mentioned earlier, we'll be sending you a copy of the presentation and recording. Please get in touch. Let us know if there are any webinar subjects you'd like us to cover. It's great to know the topics you're interested in and hear about. Feel free to get in touch or send any queries to Hamish. Again, apologise for the sound quality on this webinar. Hopefully you could still make out most of what was being said, and we'll answer your questions offline just to make sure we didn't miss anything. On behalf of myself and our presenters, thank you for your time. Enjoy the rest of the day. Thank you.